Okay, guys, so let's continue with section 3.4, the derivative as a rate of change. So let's think about today a situation like this. We have consider about we have a moving object, and very naturally we can, assign that moving object a position function, right? So at time equals t, where is the position of the moving object? And meanwhile, what is the corresponding velocity function, right, at times equals t? And also the acceleration, all right, of that moving object. Okay, so actually, those three functions, the position function, velocity function, and also the acceleration function, they have actually have a big connection here. So since we learned about the derivative, and the connection between those three is if you take the derivative of the position function, you're gonna have the corresponding velocity function, okay? And if you take the derivative of the velocity function, and you're gonna have the acceleration function, or you take the second derivative of the position function, that are gonna give you the acceleration function here, okay? And why this is true? Well, you think about it, where we get the derivative definition, you can project to get the velocity function. We first of all trying to figure out the average velocity, and then I let the time interval to shrink to one moment, which is t. That is exactly the process of having the derivative, which is right. Basically, guys, remember when we learned the derivative using the limit concept, it's limited as h approaches 0, right? Right now, what you can do is you can let limit as a small interval. Still, you can think about it h as a time interval, and then but on the top that's gonna be s of t plus h minus s of t over h. So let me write it out here. So f prime, which is exactly s of t plus h minus s of t over h. We take the limit, let h approaches 0. Okay, so this actually, if we block this part, this is gonna be the average, right, velocity between the time interval from t to t plus h. As letter h approaches 0, which you're gonna get the derivative, that's exactly, okay, that instantaneous velocity at that moment t, okay? And similarly, we can use a similar idea to get acceleration at time t, which is the derivative of the velocity function, okay? And also, for here, guys, the speed, okay, gonna equals the absolute value of the velocity, okay? So in other words, speed will always be greater or equal than 0, okay? There's no, like I'm driving negative 70 miles per hour, right? There's no way. So the speed must be greater or equal than 0 all the time. However, for the velocity, we do can have like a positive or negative, right? It depends on if I'm heading to the left as a positive, and then when I heading to the right, that stands for the negative, okay? So yeah, so this are the relationship between the position, velocity, acceleration, and the speed, and the velocity function. So now let's look at one problem here. And this problem, we're gonna understand how do we do this, okay? So suppose I threw a rock, okay, straight up. And then with the initial velocities, this was 160 feet per second. So I can't, okay? This velocity is very big. And it reaches a height of s of t equals 160t minus negative 16t squared feet after t seconds, okay? So basically the graph, it can be something like this. This is like a rock, goes up, right? It hits the highest height and then it goes down. Okay, this is the process. Okay, so here is the question here. So question one: how high does the rock go? Okay, so think about this, guys. When I throw a rock, and the initial velocity, if we think the going up, the velocity is positive, and going down, the velocity is negative. So I have an initial velocity which is 160 feet per second, right? That is going up, okay, it's positive. However, due to the gravity, as you can see that the acceleration actually is going down, right? Because that's the only force that that applies on the rock. And then since your initial velocity is going up, but you have a gravity is dragging you down here. So actually, the rock is going up, and then at a certain moment, the velocity becomes 0. And then after that, the velocity actually becomes negative. Do you see that, right? Again, if we set the top going up is positive here. So so how high does the rocket go? Well, question one is maybe that's right here. So the question one, that is when the velocity equals 0. Okay, when the velocity equals 0. Okay, then we know that the derivative of st position function, or in this problem, the height function. If we take the derivative, that are going to give us is 160 minus 32t, okay, minus 32t. And you can see that this is my velocity function. I'm looking at, okay, at what time my velocity becomes 0. So I can set 160 minus 32t equals 0, and easily you can solve that t equals 5. That means at t equals 5 seconds, after I threw the rock straight up to the sky, and then it hit the height. Okay, but how high? Okay, right? How high? And we can see, we can plug t equals 5 to the s of t. So s5, which equals 160 times 5 minus 16 times 5 squared. Okay, and is this gonna be 800 feet? This gonna be, you can compute it, it's gonna be 400, okay? 400 feet. So the height, which is 400 feet, okay, which is 400 feet. You can make the calculation by yourself, I'm pretty sure about this. Okay, so the first part is done. And then let's look at, okay, what is the velocity when s equals 256? And also, is the rock, is it going up or is it going down? Okay, so now let's maybe use this. Okay. Let's see, so this is question 2. S of t equals 160t minus 16t squared. And it asks us, okay, when st equals 256, right? Okay, so when s equals 256, what we can do is, we can let 116t minus 16t squared equals 256 feet. And then we can solve, okay, what t gonna make the rock at 256 feet above the ground. Okay, so this is gonna become a quadratic equation. So we can do a little bit of rearrangement, right? And I can factor the 16 out, which is t squared minus 10t, and then plus 16, okay, guys? And also we can do t minus 2, t minus 8. So you can get t equals 2 seconds and t equals 8 seconds. Okay. So now let's think about this. What does that mean? Remember from part 1, at t equals 5, and then my rock get its highest height, okay? And after that, it will go down. So do you agree that when t equals 2 seconds, it has not reached the highest height? That means the velocity is still going up. You see that? And then when t equals 8, it's already past the 5 seconds, which my rock going down to the ground. Okay, so first make sure that then v of t, as we see that is 160 minus 32t, then v of 2, so 160 minus 32 times 2, it's gonna give us, this is 64, so it's got 96 feet per second, right? And then v of 8, which is 160 minus 32 times 8. As you can calculate it, and I believe it's gonna give you negative 96 feet per second, okay? So at this time, my work is still going up. At this time, my work is going down, okay? So that's problem 2. Let's look at what problem 3 says. Okay, so when does a rock hit the ground? Okay, when does a rock hit the ground? Well, this problem, let's think about this. Since this st is a height, right, of the rock above the ground, okay, above the ground, and do you agree that when the rock gonna beat the ground, it only has 2 moments, right? Initially, right, when time equals 0, yes, the rock is on the ground, I have to throw it up. And then after a certain time, it hits the ground. So how do we do that? Well, do you agree that when the rock hits the ground is when the height gonna equal 0, right? Correspondingly, you have 116t minus 16t squared equals 0. You can factor 16t out. That's gonna give you 10 minus t, right? And then you can get that t equals 0 or t equals 10. Bingo. T equals 0 stands for the time the rocket is still on the ground. I haven't not threw it up. When t equals 10, 0 go back. Okay? So that's problem 3. Now let's look at use this little space to talk about number 4. So 2 is finished, 3 is finished. Look at number 4. What is the acceleration of the rock? And as you expect, it's gonna be the gravity, right? So number 4, which the acceleration function equals the derivative of the velocity function, which the velocity function is here. As you can see that it's gonna be negative 32 feet per square second square. Okay, that is the acceleration function, okay, of the rock. And for some of you who learn physics before, this is exactly like this corresponds well with the gravity, right, part. So this is second part of 3.4, and yeah, so through those 2 examples, I think you already know the knowledge between the derivative and the rate of change, right? Okay, so I'll stop here, and then I'll see you in the next video. Okay.